Good evening. Welcome back to week 10 doubt clearing session on fundamentals of additive manufacturing. I'm going to share my screen. Last class, we have talked about the wire-based additive manufacturing process. First, electron beam-based wire aim, and then laser wire aim. We have also started the powder-based laser aim. And the powder based one was mainly the powder feed one. So today we will be talking about the powder feeding technology and along with it, the powder based additive manufacturing process. If you have any doubt from the previous class, you can ask. Otherwise, I'll go through the notes first and then we'll talk about or discuss about the previous year questions. Do you have any doubt? Have you gone through the lectures of week 10?
No, ma'am.
Okay. So then brief. Yes. Okay. So briefly, I can talk about the notes and then we can jump into the question and answer sessions. I have also the same Mentimeter questions from previous class on electron beam based wire aim and powder feeding aim. So let's first start with powder feeding aim. So in case of powder feeding technology, my powder is coming through the coaxial nozzles in which the laser will come centrally, and if it's my nozzle, then my powder will come through circumferential slots. These are my powders, these two lines, and this central line is my laser, and these lines are my powder. So the powder will get focused at a particular position, and that at that focused point the laser will also get focused, and the laser will melt the powder, and when it will move along the x and y or z direction, the deposition process will go on. So powder, one thing to notice importantly is in powder delivery system, the powder is coming along with the carrier gas. So as it's coming through the pipes and it's coming from another system, this is my system of powder delivery. This is coming to the deposition zone using a pipe. That means it has to be carried out in this whole path. So my powder cannot be very small. So that's why there is a typical powder distribution, size distribution available for this process. We typically use 45 to 120 or 45 to 105 micrometer powder. So this is the typical range of the powder particles. It cannot be one particle, so it has to be some distribution. It also has some another significance how why we use distribution instead of one powder particle size that I'll talk about. So this distribution is very important because the powder is coming through the nozzle using some gas, some carrier gas. Here argon is the carrier gas that we use. As it's inert, it has some weight, so it can carry the powder from the powder feeder to the deposition zone. And the powder is having such typical size distribution range. Now, what if the distribution is lower than this? Can we use lesser than 45 micrometer powder? The answer is yes, but the same system cannot be used. So DD was invented from the process called cladding. In cladding, we basically structure the wear out or worn out part of a big shaft or components. So basically, where my whole shaft is not bad or not broken, it's just some of the portion is wear out, worn out. In that portion, I can do the cladding and it can be fixed. So from that concept, the DD came. That's why the cladding had to be done with a higher spot diameter. It's better if my deposition size is bigger, then I can end my job at a very less time. So that's why the cladding is generally done with a bigger laser spot diameter and powder. So it's okay. But if I am trying to build a component with a micron level feature size or efficiency or I mean resolution, then I have to go for lesser powder diameter. In that case, this type of system, what is been used, cannot be used in that case. We have to change the system. Even we can print nano size powder particle as well. In that, in that case, there are some vibration, ultrasonically vibration based system that we can use for the nano level powder delivery. So the discrete coaxial nozzles uses multiple jet of powder stream delivery feedstock directly to the melt pool via separate and distinct powder delivery channel. So basically, if this is my nozzle, so there is only one powder feeder. One pipe is coming from there, and then it got separated. And there are 3/4 channels, and through 3/4 channels, 3/4 jet of powder is coming from the nozzle, and they get converged at a particular point over the bill plate where the deposition takes place. I hope it's clear. So if I cut the nozzle and if you see the top view of the nozzle cross section, then it will look like this, where the central slot is for the laser and there are three holes at 120-degree apart. And from these three holes, the powder is coming. Or there are six holes or there are four holes at a constant angle apart and uniformly distributed, or it can look like there is a big hole. Sorry, these has to be circle. This is the bigger circle of the nozzle. This is a smaller circle of the nozzle. Sorry, this circle is this much, for example. Oh, I can draw another. This is my bigger circle. This is my smaller circle inside. From this hole, the laser is coming through this, like from the middle point, the laser is coming. And this slot is fully open through which the powder is coming. Here, only one jet of powder is coming. It's not multiple jet are coming and getting focused. From the whole diameter periphery of this nozzle, the powder is coming. So it's a kind of cylindrical or slit-based nozzle, you can say. So different type of nozzles are available in the market. It depends which one you are choosing for your system. So if you see this diagram, then I have chosen the two nozzle or two discrete stream of powder nozzle, and where these are the two slots through which the powder is coming. And they will come at a particular point, and this is the focus. So at this focus, if my laser is also getting focused, this is my laser, this is the focus of the laser also, then this is the part where my deposition will take place. So this will be my build plate. Then this is my build plate. So you understand? On top of the build plate, my powder and laser both has to be focused. No matter if the laser is not getting focused, we also sometimes print in defocus zone, but my powder has to be focused to get the higher deposition efficiency. Okay, so what is deposition efficiency? So basically, how much powder is getting or how much powder is coming ratio to how much powder is actually depositing the material. So if you weigh the build plate before and after deposition, you get the deposition weight. And then if you weigh the powder which is coming at a particular flow rate for a particular minutes, like 5 minutes, 10 minutes, or 30 minutes, you get how much powder is coming per second. And you have the build deposition weight, you have the powder weight which is coming. So just ratio of it is the efficiency. So deposition rate by whatever powder is coming is equal to generally 10, 20, 30% in case of powder DD. So that less efficient it is in terms of deposition, and that more amount of wastage is there. So a lot of powder gets wasted in this process. So the wasted powder will get collected nearby the deposition zone, which you can collect later on and reuse it after sieving. But if your powder is reactive to nature, like environment or oxidation or water or moisture, then some powder can entrap moisture in them and they will be waste, or they can get oxidized in a humid environment. Then your powder is also a wastage. So that's why powder handling is very important, and this wastage minimization is also one of the concern of powder DD process. So this is the design consideration. So now this angle is very important. This angle, because based on this angle, it depends whether forcefully you have to provide the powder in the deposition zone, or after reaching the nozzle, the powder will automatically come to the deposition zone because of gravity. So based on this angle, the more the angle is, the powder can come automatically out of the gravity. But if the angle is very steep, then also it can come. But if it's nearby 45 degree or so, then you need to have a forcefully argon gas to carry the powder. It will not come automatically out of the gravity. So that is the fundamental thing. So that's why it's important to choose the angle. It's important to choose the powder distribution instead of one particle size. So what happens is, draw here. So for example, the powder is coming and this is my bill plate. Okay. So if this is my bill plate and these are the powders, and this is a distribution of powder which is coming. So many size distribution is present, you can see. So it says that when one layer is built, now the second case where one layer is built. So this is my one layer. What is that? This is my one layer. Okay. Now, for example, if this is the layer, next on top of it, the next layer will come. So when the deposition is happening, the bigger particle size will try to fill up these gaps. I don't know what is that. So the bigger particle will fill this undulated zone and the smaller particle will fill the voids. So that is why there is a constant distribution, Gaussian distribution, instead of a one particle size range. So this is the reason. I hope it's clear. So if you choose only one powder size, then there will be void in between. But if you have a distribution, then you can fill the voids with the smaller size powder particles. So that's how you choose the size distribution instead of one particle size, so that you can fill the void and there will be less porosity in the deposition because there will be less space available in between the powder particles. So that is the concept. So now we have the answer why we have a distribution instead of one particle size. Now the third point is this convergent point. As my powders are coming through multiple jet or stream, they are coming and meeting at one point. Now they are powder particles. They will spread after coming through the nozzle, because in nozzle they are highly pressurized. They are being carried with the argon gas. But when they're coming out of the nozzle, they are free. So that's why they will try to expand. So as a result of which the convergence will not be that sharp as what you get in case of laser. In case of laser, if you are converging the laser using a lens, it's very sharp point, convergent point, focus point. But if it's a powder, physical powder particles, they will not be a very sharp, less diametric convergent point. So there will be a spread. So now this is the spread. This is stream 2, stream 1, 2, 3, 4. And they are meeting at this point, and this is my convergence zone. And if my laser is this much, then only
Um,
this, yes,
this stream 1, stream 2 are all those powders.
yes, this is one stream means this is the powder.
Okay.
This circular के अंदर powder है.
Okay.
This is the spot of the powder. So now if this is the red is my laser spot, okay? Now let's understand this clearly. This is the overlap zone. I can clearly see the overlap zone. This is the overlap zone 1, 2, 3, and 4. And I need all my powder stream to overlap one onto each other at the laser focus spot. So in the laser focus spot, only this much, this petal-like structure, these two petals are actually the overlap zone, and this much is the complete overlap between four streams, and the laser spot there is this much. That means now when I'll try to deposit the material, the deposition rate will be very less, because at the focus zone of the laser, there is not much powder. The powder is scattered. But on the other hand, if you look at this picture, then they are very tightly focused together, like the stream 1, 2, 3, and 4 are tightly focused together, so that their overlap zone is very high, very large, and their overlap zone where all four streams are getting overlapped is also very large, is this much. And in between this red spot is my laser focus spot diameter. So inside laser focus spot diameter, all my powder particles are coming, whatever is coming from this four streams. So that means when I'll try to deposit, these powders will also get fused together because of the high temperature gradient and the heat of the laser. It's not like itne se jagah pe hai to this much powder will be fused and this much will not be fused. So some of it will also come in the deposition because of the denudation as well. So that's why my deposition rate will increase. Means more number of powder particle will actually participate in the deposition process. So my deposition weight, if I measure the weight after the deposition, it will be higher. Sorry? Do you have any doubt?
After the deposition, how can it be higher, ma'am?
Uh, After the deposition, how can we?
No, you have said like after the deposition rate will be higher, right?
Yeah.
Like that
How?
means during deposition only this deposition rate is significant, isn't it, ma'am?
Can you be a little bit louder?
Ma'am, is deposition rate significant only during the time of deposition, or after that also will that term be
Okay,
significant?
so deposition rate means how much powder is actually participating in the deposition. So if this is my scenario, which is the scenario B, then more number of powder particles are participating in the deposition. That means if you weigh the depositing material, it will be more than the wastage. because in both the cases, same amount of powder is coming. But here, more number of powder will be actually melted and solidified. That means more deposition. Like the deposition bead, deposited part will be thicker. It will have more width. It will have more thickness. Less
Because
powder
is
will
it
be
because
wasted.
laser size is more in the second figure, is it?
No, it's like the so there are two things. One thing is here I am keeping the laser focus spot as same. Just imagine the laser focus spot is same, this much only. But here the overlap of the powder stream, you see all the powder is getting overlap at this zone where the laser is getting focused. But here it's not like that, right?
Yeah, in the
If this
second
is
figure
my,
it is more dense.
yes, because the overlap of the stream has taken place in such a way. So that is one scenario. Okay, in which this is the more deposition I will get from the second picture. Another is already I am getting so big overlap zone, I can actually increase my laser spot diameter as well to get even higher deposition rate. Means even lower wastage. So that's how it works. Understood?
Yes.
Yes. So this is the concept by how we can see that how important it is to tightly focus the powder streams at a particular spot to get the higher deposition. And also, as you mentioned, if it's more laser focus spot diameter or not. So there are settings in the laser lenses. By changing the position of the lens, some machine has the option to increase the spot diameter at the focused position. I'm not defocusing the beam. At the focus only, I can increase the spot. So in this case, in case number one, even if I increase the focus spot diameter, my powder still will be wasted. But if I increase the focus spot diameter in second case, I can increase lot more. I can make the process more efficient because the powder is very tightly focused at the middle point. Next is the FGM fabrication. FGM is functionally graded material. So that means if you have a part like this, you have some property at the bottom, you have a different type of property at the middle, and you have completely different property at the top. Or you have different property at right hand side and different property in the left hand side. So this property change, how you can achieve. One is you can mix powders. So basically, for example, you are making alloy where two or three different metals are coming. For example, SS, aluminium, copper, and nickel is coming. And these four are making a functionally graded material where in this portion nickel is more, in this portion copper is more, in this portion aluminium is more, and in this portion SS is more. So when developing the bead itself, we can control the powder feeders in such a way that we can deposit the material, the powder is getting mixed together, but at some portion some metal is more. So depending upon that, we can get some different property in the whole part. So that is how you can print FGMs. And functionally graded material printing is way more easier in case of powder DD technique. As we are handling with powder, mixing powder is easier. So that's why FGM is a very good example of application of powder DD. discrete coaxial nozzle. In case of discrete coaxial nozzle, if you are delivering the powder in this type of 1, 2, 3, 4, or 6 nozzle, then you have to make sure if your head tilts at one angle, your powder feeding should not be hampered. Like if you see this diagram, the first case, there the powder is also getting affected by the gravity because of the tilting of the head. But in this case, in case of this discrete nozzle, this 3, 1, you can feed more powder in third number of nozzle, so that my powder delivery will be constant, uniform, even if you tilt the nozzle. So that's why uniform in this case, if it's uniform type of cylinder feeding system, feeding nozzle, then this discrete nozzles will help me in getting a very uniform powder delivery, even if your head tilts at 45 degrees or more. So now we can talk about another very important thing, that is the laser point of view. So in this case, if you see, the laser is coming. This is the focus spot diameter of the laser. And this is the zone of interest. Like this, the laser is penetrating this much and giving me this zone. So in this case, the middle part will have more depth rather than the edges, because my laser is having a Gaussian heat intensity profile. The heat distribution in the laser is like this. At the edges, it has lesser intensity than at the middle. At the middle, it has more intensity. So it's called the Gaussian beam. Gaussian is a type of graph where we get the maximum number or intensity at the middle, and in the edges, it slowly exponentially decreases. So this is the most natural graph you can find in nature, in human body, in everywhere. So that's why when laser emits, it emits like a Gaussian beam. So this Gaussian beam, if you're using for cladding or any additive metal AIM process, then you'll get the heat distribution effect in the melt pool. That's why your middle part will be deeper than the edges, and thus you get the parabolic shape of the bead or parabolic shape of the heat affected zone in the melt pool. And it's constant for any cases. So this is how you can uh, feed the powder so that your laser focus spot covers the stream of powder which is coming, so that your deposition rate should be higher. So always remember, the main problem related to powder DD is the wastage, because the powder will flow, the powder will fly, and the wastage will be more. So that's why, to regulate the wastage or to minimize the wastage, it's important to find out what is the optimum position of your deposition, or what should be the optimum position of your deposition, and what should be the optimum laser focus spot diameter for your deposition. Okay, if you have any doubt in between, you can ask me. In this case, if you see, there are two peaks. So this peak is basically the laser intensity, or this is showing us the laser intensity peaks. Okay. So here it's like only one peak which is very sharp. Gaussian, like not exactly Gaussian. Exactly Gaussian will be somewhat like this. And this peak is very steep, so somewhat like Gaussian. This is not near Gaussian because it has Gaussian like till here, and then at the middle it has very sharp peak. Here it's two peak, here it's more significant to fix. So these are different intensity profiles that you can use for DD. And let me tell you one thing. It's uh, it's proven by literature that when you use this type of peak, your deposition rate increases because you actually entrap the whole powder inside this zone. And at the edge, your laser is coming, so your deposition rate increases rather than the Gaussian weave. So these are few studies people are doing so that you can optimize the deposition rate first, which is the main problem in D. Also, DD sometimes, like most of the time, you can find the DD machines which are open machine. So if you are working with reactive materials like titanium or aluminium, which is very prone to get oxidation, in this case, it's very important how you're regulating the argon gas flow. It's very important that your argon gas flow should be optimum to minimize or to avoid the oxidation, or as argon flow is there, so quick solidification is also there. So during solidification, there should not be any cracks. So these are few things you need to note down. There are various process parameters as well. So now comes the different type of powder feeding technologies for different size powder particles. So already I have told you that nano powder is a bit tricky. So that's why there are various type of design in the delivery system. So it's non-pneumatic nozzle, very popular design, then non-pneumatic nozzle. So these are basically one example I can tell you is if there is a sonotrode which can give you the ultrasonic vibration to this nozzle, then your nozzle will deliver the powder only at that time when you touch the sonotrode here and your ultrasonic vibration is transferred to the nozzle. And at that time only your powder will come, and other time the powder will not come because it's nano powder. It will be clogged inside, it will be stuck inside, and when you touch the sonotrode, so basically when you give ultrasonic vibration to the nozzle, the powder starts flowing, starts coming in the deposition zone. So this is one example of this non-pneumatic. There are other systems as well how you can regulate. So you can go through the lectures and there are videos of how this vibration based systems work, how this rotation based disc based systems work for powder feeding. So I think these are the type of this is all about powder DD. So in this photo you can see 4 stream of powder is coming. If I zoom the picture, see 1, 2, 3, 4. 4 stream of powder is coming, meeting at this point. From the middle, the laser is coming like this, which you cannot see because the laser is in infrared region, which is beyond the visible range, and the cladding is taking. So cladding here, it's like a cladding, like a coating of few layer on top of a shaft to repair or to protect it from environment. There is something called hybrid system also. So after cladding, just after cladding, you can move it to the hybrid tool where you can do the milling or face milling or grinding, drilling, everything to get the final geometry. So these are few type of nozzles. That one is 45-degree nozzle, 60-degree nozzle. As I said, one is used where carrier gas is needed must to flow the powder. In another case, the gravity is enough to flow the powder after it reaches the nozzle. So these are few parts printed using layer powder DD. One very important thing, as I am also working in the same area, powder DD is way more or way tougher than wire DD because it's very tricky to control the process. It's very tricky to control the powder flow, to minimize the wastage, because in wire DD 100% is the deposition rate actually, but in powder it's not like that, it's 30-40%. So that's why it's more tricky process, but it has lot of scope for improvement, and people are also using powder DD for part development, for precision, because rather than wire in powder you can get actually better precision. So yeah, these are the things related to the powder feeding aim technique, which is coming under the big umbrella of state of the art called directed energy deposition. Now we are going to talk about the powder bed based AM. Before it was powder feeding. Right now it's powder bed. Powder bed means there is a bed which is the substrate. On top of the substrate, the powder is coated already. The loose powder is spread over the bed. So that's why it's called powder bed, which is coming under the state of the art called powder bed fusion. So in powder bed fusion, there are different segments. One is SLM, selective laser melting. One is SLS, selective laser sintering. In this case, vacuum-based system is quite difficult to be used, but still people are doing it. So electron beam based powder bed fusion is also there. Laser based powder bed fusion is also there. Arc based is not there. Plasma based is also not common. So electron beam and laser are the two type of energy source that are typically being used in case of powder bed fusion. Now we are going to start this thing. So I think both of you are present here. So I can start with the Mentimeter as well, because then we will come back to the powder bed technology because it's a new technology. So if you are okay, then we can start with the QR code scanning. Should I start with this or first complete this and come to the question answer session? Today's Mentimeter questions are from previous class on which you have already attended the quiz.
Week 9, is it, ma'am?
Week 9, yes, week 9 topics. I think we can go with it. So you can scan the QR. Just a second, just a second. Have you scanned the QR?
Yes.
Yes, okay. We can start. This is your first question. In powder laser, DD, the laser primarily serves to It's very easy. Yes, to melt the powder and substrate simultaneously. So here comes our next question. Whoever has joined right now, you can go to menti.com in Google and use this code to join this meeting. It's a simple quiz. There is no marks related to it. Compared to powder bed fusion, powder laser DD typically offers higher deposition rate, lower resolution. Now here, deposition rate means the part size. So in DD, you can definitely produce larger scale part easily compared to powder bed fusion. A lower resolution because 2 points. One first is the powder distribution itself is bigger in case of DD. So if your powder size is bigger, that means your minimum feature size cannot cross or cannot be lesser than the powder size, the biggest powder size. Then another point is in case of powder bed fusion, the laser focus spot diameter is also lesser. So the minimum feature size actually depends on both the powder size and the size of the laser. So if the laser focus spot diameter is lesser, that means the resolution is higher. So that's why DD is lesser resolution process than powder bed fusion. And also PBA for powder bed fusion is the highest resolution process in any type of aim. So just remember this point. Okay. Next, we have our third question. Yes, laser power and scan speed. We have our fourth question. The key challenge unique to powder laser DD compared to wire DD. Unique challenge. It should not be the common challenge. Yes, porosity due to gas entrapment, and this porosity is coming because of the powder, not the wire. We have the next question.
Question is not visible.
Question. Are it? Maybe there was some mistake. No problem. We can go to the sixth question. It's coming. It didn't come. In powder laser, DD cladding efficiency is defined as the ratio of Voted already. Deposited material mass to the powder feed rate. We have another participant. Okay. Let's go to the next question. 7th. A typical advantage of powder laser DD over powder bed fusion is one-site repair of high-value component. So that is the main application of powder DD. Near net shift with very fine resolution is the advantage of powder bed fusion over DD. And no need of post processing is not even applicable to any type of additive manufacturing. So one site repair is the application, typical application of laser DD, which is called the cladding. What is wrong? Here comes our 8th question. So the dilution zone in powder laser DD refers to the mix of substrate and deposited material at the interface. No, it's not the overlapping beads. The overlapping bead is the overlapping zone. Dilution is the mixing of one layer to the previously deposited layer. So it can be mixing of deposited layer with the substrate or one deposited layer with the previously deposited layer. Who is correct? Who is wrong? Okay. Next question. The main reason EBUM requires a vacuum chamber is to ensure the electron beam stability and avoid scattering to prevent spatter ejection. No, not spatter ejection. Ejection will be anyway not spattered to reduce wire oxidation. So wire oxidation is reduced because of the vacuum. The vacuum is not made because to reduce the oxidation. The vacuum is maintained so that when the electron beam is coming, basically the beam is made of electrons which are very lightweight, very uh, lightweight. So they will not get scattered because of the air particles. Because anyway, any air particle like oxygen, nitrogen, carbon dioxide, everything will be heavier than electron. So if the electron uh, uh, attack air particle or it interacts with the air particle, it will get deviated from its path, from its focused path. So you will not get the very focused electron beam. So whenever you are working with electron beam based system, you have to have a very high vacuum chamber. Otherwise, your electrons are very lightweight particles. That's why. And in return of which we get the reduced oxidation as it's vacuum. So it's like an advantage. It's not the cause. It's not the reason. 10th question. Compared to laser wire aim, EV wire generally provides so lower resolution and higher deposition rate. Next, we have the next question. Typical drawback of EV wire. No, it's the requirement of vacuum chamber limits the part size. Lower deposition efficiency is not that true because it's wire based. So deposition efficiency will be higher. But because of the vacuum chamber, the part size is a limitation. You cannot print bigger size parts. Next, we have the 12th question. In EVM, the bead geometry is more strongly influenced. It's basically the wire feed rate and the beam current. Yes, correct. 13th. The typical cooling rate in EV is compared to DD is lower due to larger melt pool size. Also, it should be the cooling rate should be lower because of the vacuum. Because it's vacuum, there is no argon flow. Because of the argon flow, also you get higher cooling rate because it's working as a coolant. But there is no coolant, so it should be lower, the cooling rate. Next, we have the 14th question. So it's a tricky question. It's not directly related, but as the thing is going on in vacuum, so that means titanium will be easier because there will be no oxidation and reaction as it's a reactive metal. Next question. Compared to powder laser DD, it easily offers higher material utilization because it's wire based. So obviously, the deposition rate is near 100% and faster deposition because again, it's vacuum in vacuum. So the contamination and everything is lesser. Chances of oxidation contamination is near to zero. We have the second last question. It's laser wiring, not EB. Yes. And here is our last question. It's nearly 100% material utilization because it's wire feed aim and higher deposition rate because it's wire feed. Okay, here is the end of the 20 Now we can go back to the notes. Now we can go to the powder bed. Yes. So in case of powder feed, we were having the laser power, beam diameter, beam profile, working distance, laser wavelength. These are the process parameter. However, the laser wavelength is a very important process parameter because it directly has a relationship with the absorptivity of the metal in the process, but we cannot change the wavelength very often. If you're using a system, you're using one type of laser. So actually you cannot use or you cannot change the wavelength. But if you can change the laser itself, then you can change the wavelength. For example, there are few different type of lasers present in the market. One is IR laser. So IR laser means its wavelength is in the near infrared region. So that means the wavelength is near to 900 nanometer to 1064 nanometer or 1074 nanometer or 1100, 1500 till 1500 nanometer is the NIR range. So that is the one laser that you are using for one system. It has a direct relationship with the absorptivity of the metal of that laser in a particular metal. Like the aluminium absorbs IR laser lesser than what the stainless steel absorbs. So that is also playing a very important role. But when you change the laser, for example, blue laser, it has 445 nanometer wavelength. That means its absorptivity is way higher in case of any other metal. So your whole process parameter set will be changed. So these are the parameters. Then the feeding. So in case of feeding, the nozzle type, the powder flow rate, the gas flow rate are important. As I said, gas flow rate to maintain the process contamination free. Nozzle type, so how many streams of powders are coming? Is it 3 stream, 4 stream, 6 stream, or continuous ring type? Powder flow rate is also important. So the carrier gas is carrying the powder. So carrier gas flow rate is actually the powder flow rate. So these are the things related to the feeding of the powder. Now material design. So that means material of the powder, composition of the powder, diametric distribution of the powder, shape of the powder. It has to be spherical. Otherwise the compaction will not be good. Then the material of the substrate, heat treatment of the substrate, whether you have done the heat treatment, like how conductive the substrate is, the geometry of the substrate, the geometry of the deposition region. So these are the material and design perspective. You can see motion and path is like motion is basically whether it's a 3-axis CNC system or it's a 5-axis system, or in case of a robotic system, your head can move. So whether your head can move in how many degrees of freedom, then when your head is tilting, your powder flow should not be disrupted. So these are the things. And for path, basically the overlap percentage is the hat spacing. So the hat spacing is one uh, important process parameter. Then comes the uh, layer thickness, another process parameter, preheating temperature. So in case of laser or any type of AIM process, if we are dealing with metal, then preheating of the substrate is important to minimize the residual stress and to make the process more efficient. The interlayer dwell time. So in between layers, sometimes we put some dwell time so that the previously deposited layer can be cooled down, so that when it's cooled down, your deposited the next deposited layer property will differ depending upon this dwell time, because when it's very much heated and then you're printing the next layer, the oxidation chances of oxidation is more in case of reactive metals. So dwell time is important in that in those metals. Now this is the laser cladding principle. So we have already talked about these things. The angle I have already talked about, whether it's 60 degree or 45 degree, depending upon that, you will get the powder flow, the nozzle, whether it's gravity based or forcefully carrier gas. Catchment efficiency is the mass of the clad layer by the powder mass which is ejected from the nozzle. So then comes the catchment efficiency in terms of the temperature and other heat transfer model to use, so that you can get what is the bead profile, and for this much bead height and depth, how much power was coming and how much powder was coming. So it's depending upon that. So that's why for catchment efficiency, you get a very bigger equation. Don't need to remember, but you can write. So this equation is important. You can note down this equation because it actually can come in your exam, because I have the previous year question on this equation. So it basically says that if you have two type of, so in your powder feed based aim process, off axis nozzle is used to fill the material in the pool. If it's set up, the laser power of the materials change to from one A to B if the melting point of the material A and B is same, but the thermal conductivity is different. Thermal conductivity of B is 4 times higher than the thermal conductivity of A. Then the ratio of catchment efficiency will be the square of it, basically. The reverse and square of it. So you get this equation, at least this much is important. Depending upon this formula, you can get the sum. I have some sum in the previous year question. They are a different zone of the processing, they are a different zone of the deposition, and we have already talked about this. This is showing that when I have told you that the laser will be in Gaussian beam, the laser will have the Gaussian profile. Other than laser, the powder which is coming will also have the Gaussian nature. So if the powder is also having the Gaussian nature, that means at the middle, the number of powder particle will be more than what you can find at the edges of the laser beam. So that's why also your bead profile is generally like this. Lesser depth at the edges than the highest depth at the middle. These are the related sums, so that's why I'm not going into deep of this. This is related to the bead profile, how much should be the overlap percentage. One thing is your bead should not look like this. Your bead should look like not even look like this. Your bead should look like this. Parabolic, completely parabolic. Otherwise, when you print the next bead, you get the porosity here. The bead should be parabolic, and then you print the next bead like this and the next layer like this, so that you don't get any porosity in any junction. So that's why the overlap percentage and the layer thickness is very important in this process. So when we optimize the parameter, we first print one single layer with this overlap beads, and then we measure what is the height of this bead, and then we fix the the layer thickness depending upon the thickness of this first layer. So this is the example of the FGM that I have told. FGM means functionally graded materials, where you can find different density or different property at different locations. So density based FGM is one, material based is another, color based is another. So color based we are not talking about here, but density and material based we can definitely talk about, because material based is basically if you are mixing 2-3 powders, you can differently mix these powders at the time of deposition, because you are talking about the powder feeding technology. And if you are talking about the density, that also can be done. So in case of lattice structures, you can take help of lattice structures to print the different density parts, like the parts with different density at different locations. So then comes the same thing. So this is the example of cladded layer of Inconel 625 on the chromium molybdenum steel. And this is the grid-based system structure which you can print easily using this DD technique. And using this type of lattices, you can decrease or increase the density at different locations. So I think you have these two PDFs only for week 10. Can you confirm? Oh, do you have any doubt? No? Then I can talk about the question answer of week 10. So these are the previous year question of week 10. The first question. In a powder feed based aim process, an off axis nozzle is used to feed material into the molten pool. If the material is changed from A to B and the setup is used with the same process parameter, the melting point of material A and B is same, but the thermal conductivity of B is 2 times higher than A. Then the ratio of catchment efficiency. So as I said, it's very important formula. It's just the opposite and the like inversely proportional and square of it. The answer should be 4. Then in a powder feed based aim process, an off axis nozzle is used to feed material into the molten pool. If the powder of the laser is increased by twice, then the catchment efficiency will increase by, so it's again straight proportional and square of it. So the answer is 4. Because the laser power is increased by twice. So that's why it's 4. Then I think it's in a powder feed based aim. So it's again the same question with the different digits. Like here the thermal conductivity of B is 3 times higher than A. So the answer will be 9. In a powder feed based aim process, I'm talking about this second question. Off axis nozzle is used to feed material into the molten pool. If the power of the laser is increased by 3, then it will increase by 9 because it's the square of it and straight proportion. In a powder feed aim, the off-axis nozzle is used to feed material into molten pool. If the diameter of the nozzle ejecting the powder is 10 mm and the ejection angle is 30 degree, the angle between the vertical axis and the powder delivery. So this find out the projected area. So this is the formula. So the projected area will be pi r square by cos theta. Theta is the ejection angle. So that's why I said ejection angle is very, very important and one sum you can expect. A coaxial powder delivery nozzle follows a Gaussian distribution of powder particles in 2D. Find out the particle number concentration at point xy in the cross section of the stream. Assume N naught as peak particle number, concentration at the stream center, sorry, and R are as the boundary radius at which the particle density is high. So it's the formula, and the correct answer is this one. It's the same question, so I'm not going through it again. So it's basically, I have the previous year and previous to previous year question, 2-year questions all bunched together. So that's why I have few questions in common to show these are the most important questions. Now, the powder feed based aim with a coaxial powder delivery if the radius of the powder stream at the surface of the substrate is 3 mm and the diameter of the molten pool on the surface of the substrate is 6 mm, then find out the primary efficiency of the process. This is the formula, you have the answer. Then the powder feed based aim process uses a coaxial nozzle delivery, powder delivery. If the shape of the cross section of the deposited bead is parabolic, of with 2 mm height, 3 mm, find out the cross section. It's 2 by 3 of width into height. The answer is 4 mm square. What is the most significant use of a slim nozzle, long powder delivery nozzle? So it's because of the better accessibility. Because if you see the typical size and shape of the nozzle used in cladding, it's quite big. It's quite thick. It quite look like this. So if you want to print, if you want to repair a very small accessible portion or something, you cannot insert this big thing inside that. So that's why these small delivery nozzles are used to access the pinpoints or a very small portion for cladding or for high resolution or small feature size parts. What is the primary characteristics of functionally graded materials? It's gradual variation in composition and or properties over the volume of the material. In the context of grid steepened structures, select the correct. So it provides high strength to weight ratio because grid stiffened like the lattice structures. So lattice structures are used to lower down the density because you are removing some of the material from some of the parts. So you are tactfully introducing some structural porosity in your part. So you are minimizing the weight. So you are reducing the weight, but the strength is increased. So strength to weight ratio is increased. Sorry, did you say anything? A low powder ejection angle results in longer depth of focus. In the context of powder delivery system, consider following statements and choose the correct option. Statement 1 is high mass flow rate is often results in increased surface roughness. Statement 2 is high mass flow rate is often results in increased crack porosity. Okay, there is another option coming right now. So here both are true. High mass flow rate is often results in increased surface roughness because if I'm talking about powder, then if the mass flow rate is higher and you have a this much amount of powder can be only melted and solidified, and if your mass flow rate is higher, that means you are providing more than necessary powders, then they can get fused together and give you surface roughness. And also it can increase the track porosity because of the inter particle interaction in the melt. Then the powder particle concentration at the focal point in the coaxial nozzle with laser beam at the center follows a linear trend. The head tilt of continuous coaxial nozzle over 45-degree results in non-omnidirectionality. If you remember that head rotated at one angle, so the powders were coming more dense in this portion and there was very less powder in this portion. The powder was coming like this. That same thing. Discrete coaxial nozzle uses distinct powder streams with appropriate inclination to delivery powder whereas a continuous coaxial nozzle in the powder is delivered to the melt pool in annular flow pattern. In the context of centrally feed nozzle, consider this two following statements. It generally results in insufficient heating at the edge of the melt pool and excessive heating at the center. The catchment efficiency of centrally filled nozzle is comparatively higher than that of the coaxial nozzle. Only two is true, that the catchment efficiency of centrally filled nozzle is comparatively higher than the coaxial nozzle, but it generally results in insufficient heating at the edge of the melt pool is not correct. It's a well-known technique of centrally feed nozzle system, so it's wrong. With reference to continuous coaxial powder delivery nozzle with a central beam, consider the two states. At higher inclination, the drag velocity of individual powder stream can be appropriately adjusted to restore omnidirectionality. It is not true in this respect. The continuous coaxial nozzle leads to higher substrate dilution at the center compared to the edges. It's because of the type of the laser beam, intensity of the laser beam, also the powder distribution at the focus point. The optimal range of the dilution ratio between the first layer and substrate is it's near to 10 to 30%. The discrete nozzle, coaxial nozzle, a decrease in powder ejection angle leads to the increase in standoff distance. Consider the following statement and choose the correct option. One is global energy density is used to investigate the interlayer porosity due to track fusion keyhole. It's true. The region with high GED are subjected to lack of fusion. No, it's not true. Some question from last to last year. FGM stands for functionally graded materials. Grit stiffness provide high strength to weight ratio. Which of the following is not applicable for powder feed based AVE process? Its part resolution is not, it's good, but part restoration is the most significant application of powder feed based cladding. Powder feed based AIM is also known as cladding. Surface alloy is also one application of cladding. In continuous coaxial nozzle, the powder is delivered to the melt pool in annular flow pattern, whereas the discrete coaxial nozzle uses the distinct powder streams inside the nozzle. For a discrete coaxial nozzle, the increase in powder ejection angle leads to decrease in the standoff distance. For discrete coaxial nozzle, the diameter of the powder stream's focal point should be larger than the spot size of the laser beam to ensure omnidirectionality. Select the correct statement made in the context of coaxial powder delivery. So the coaxial powder delivery nozzle leads to high substrate dilution at the center as compared to the edges. Select the incorrect one. Carrier gas impact high velocity of the powder particles. Acoustic vibration can be used for powder delivery. Yes. Ultrasonic vibration can be used for. Yes. Water bath can be used. Yes. Carrier gases impart high velocity to the powder particle is not true in the context of vibration assisted powder delivery, because there the carrier gas is not used to carry the powders. Select the current sequence. So first build the bottom and vertical walls. Switch off the laser, fill the duct with the loose powder. This is context to some rectangular duct, manufacturing a rectangular duct using laser-based powder. Then we will go for the switch of the powder, switch on the laser, then center the top layer to fill of filled powder by laser beam. Lastly, switch off the powder and the laser to build the overhanging wall. The powder particle concentration at the focal point in the coaxial nozzle with laser beam at the center follows the Gaussian trend. Select the incorrect statement in the context of continuous coaxial nozzle in powder feed-based air. At higher inclination angle, the drag velocity of individual powder can be appropriately adjusted to restore the omnidirectionality. Which of the following is not a limitation of pneumatic feedstock powder handling system? Unable to fabricate function is rated. No, it's not a limitation. It can fabricate, like cladding, or the concept of DD is applicable even if your powder is small for manufacturing FGM. And which of the following expression is true? So the global energy density GED is equal to P by VD. It's also called as line energy density, which is the P by VD. That's all about the question answer from previous year. If you have any question, you can ask me. Otherwise, you can tell me, because as it ended early today, we can talk about some other topics if you want. Or we can stop the class here. Do you have any doubt?
Ma'am,
Oh?
I'm yet to go through the lecture video. After that, I will.
Yes, you can. You have to go through the lecture videos, then only you can find out what are the doubts, because it's a very small lecture video. The lecture videos are very small and it's comparatively easier because only one topic is discussed, which is the DD. So that's why, or powder DD. I think it's easier. First go through. If you have any doubt, you can contact me anytime. Okay, then I'm stopping the class here. Thank you for joining. Happy Shubh Navratri to everybody.
Same to you, ma'am.